Like I said, I feel like at this point you should either be done or maybe stuck, and either one is okay right now. So I drew you this nice picture and a little representative rectangle of what these I guess they'd be right-sum rectangles might look like. And so we are instructed to find the area. And as I told you earlier, I'm not going to get too hung up on finding the area. I at least want to set this up. Let's make sure we're setting it up right using the limit process, also known as a Riemann sum. For that region, we can see down below with those boundaries. So I mentioned this last time. I'll mention it a couple of more times today. I feel like the easiest way to approach this is to do the really easy stuff first, and then do the medium difficult, and then do the more challenging stuff at the end. So for me, if I see that I'm going to be doing a Riemann sum, I'm automatically going to write down the limit as n goes towards infinity of sigma from I equals 1 to n. Sometimes the I will be a j or a k or something like that, but it's some element like that. To me, that's the easy part, because every single Riemann sum we're going to do is going to have some element like that, right? Then, in my opinion, I think that the next easiest thing is to start to write down either the base or the height of the rectangular areas we're going to be summing up. And in my opinion, the base is the easier of those two. So what I see over here in my picture is that my region goes from 1 to 2 right there. And so the full distance is 1. So if I was going to take that distance on the interval of 1 and divide it up into 5 intervals, wouldn't the width of each rectangle be 1/5? And if I was going to divide it up into 20 rectangles, each width would be 1/20th. But I don't want to do that. I want to be flexible and use n rectangles. So how wide would each rectangle be in that case? 1 over n. Yeah, it's just the full interval width divided by n. So my base of my rectangles would be 1 over n. So to me, that's the medium part. You got to think that through a little bit. Now the harder part is the heights. Wouldn't it be fair to say that the height of each rectangle is determined by the y value of the curve? The height of the rectangle determined by y value of curve. You can see it right there in my picture. It's right there. Height of curve tells the rectangle how high it gets to be. And of course, the y-coordinate, the y-coordinate is given to us right at the top there. F of x is equal to 4 minus x squared. So if I wanted to put f of x in there, I could, but why not just put this? 4 minus something squared. So that's going to be the y-coordinate. Now the only thing that remains is probably the toughest part to visualize, and that is the input that's going to help us figure out the y. And so I'll come back over here to the picture, and I always start with this. What is the lowest conceivable input for my region? 1. It's right there. That's the lowest it could possibly be. So I'm going to say 1 plus, and then I'm going to move from left to right, and every time I move from left to right to get to a new rectangle, to a new input, if you will, I've got to add a certain amount. What do I need to add? I think it'd be 1 over n. But then remember, we have to put that element, the summation element in there, so that we can progress from one rectangle to the next. Okay. What do you guys think? I have a question for you. How could we have done this really in the exact same way, but had a very different looking input? It would still be correct, what I'm thinking of, but it would look pretty different. Any suggestions? No, I'm just looking at only the thing in the purple box. The whole thing, we're going to find out in a second, is equal to a definite integral of some kind. But I'm wondering if you can think of like just a backwards way of thinking about the input, because there's another way you could do the input. Hey, there we go. 2 minus 1 over ni. So the question I asked you guys at the start was, what is the lowest possible input? And you all said 1. And we added 1 over n plus another 1 over n to move our way across the picture. Well, what Brandon was thinking was start from the right, then move over to the left by subtracting. I think we'd end up with the same thing. Same concept for sure. That make sense? You know, I think you would be well advised to use this way of thinking. All the multiple choices that I've ever seen start on the low end and work their way over to the right, but I think that would be logical as well. Okay. Any questions? Anything else from you guys? Go get a drink if you need to. So sometimes people think it's like the imaginary unit, right? Like square root of -1. It's not. What it is it's the element within the summation that goes from 1 to 2 to 3 to 4 to 5 to 6. And so the reason why it's in there is if you think about what it's going to do as I goes from 1. So like let's say we start off with I being 1, so it'd be 1 plus 1 over n. That would move us over to our next rectangle. And then I would be 2, so it'd be 1 plus 2 over n. That would get us over to the next rectangle height. Okay. 1 plus 3 over n. We just multiply by that I. So it literally is multiplication. So it's just 1 over n times I. And as that I moves up from 1 to 2 to 3 to 4, we get a move from left to right across our picture.
So is that like the number of rectangles or just the rectangle that you're talking about?
So n is the number of rectangles. I would be the one that we're currently thinking about. So if I said, like to kind of piggyback off what I said at the start, if n was like 20, that means that we're going to be using 20 rectangles. Mm-hmm. And then, so that means I would go from 1 to 20. But if I said, right now I is 3, that means I've moved over to maybe like the third rectangle. Mm-hmm. If I was 4, I'm talking now about the fourth rectangle's height, et cetera, et cetera.
Okay, so like only the area of the fourth rectangle would be like when I equals 4.
What are you, so like if you...
That makes sense.
Are you sure?
Yeah.
So like, I'm not going to look at it piecemeal like that, although you could, like if you wanted to, like if we were going to do 20 rectangles, couldn't you say, okay, well when I is 1, here's what I get out. When I is 2, here's what I get out. In that sense, yeah, each of the terms would represent a rectangle's area here, the next rectangle's area, the next rectangle's area, and because it's a summation, we add them all up. Okay. That's true, yeah.
Where does the 2 come in? Like
The which one?
The x equals 2, like the right-hand limit. How do you know when it stops? Because if you're finding the area from 1 to 2.
Yeah, sure. So, so I is going, like you can think of it almost like a limit. So I is going from 1 to 2 to 3 to 4 to 5 to 6, right? And so that 1 over n would go from 1 over n to 2 over n to 3 over n to 4 over n. So I'll just put it in here like this. Sorry, I'm using the highlighter. Plus, so these are all, let's just say pluses, because we're adding that on. So in the end, wouldn't it be plus n over n, so to speak? And what is 1 plus n over n? 1 plus 1, 2. That's where we end. Yeah. Sorry for the fuzziness of all that. Great questions. Anybody else? Okay. Fantastic. So then what we're going to do now is this. We're going to look at this. So the intro video talks about this. And I don't know if you guys thought about this at all, but this right here, I do want to just tag on to what the intro video said a little bit. If you've ever thought about this, it's pretty astounding. Like we've worked with this indirectly. We've just worked with this directly. But then in the end there, we just go, oh, it's equal to this definite integral thing. It's like a really astonishing thing to say. If you want to see like a proof of that, I'm just going to encourage you to take a class called Real Analysis. If you get into college and you're doing a bunch of math stuff, real analysis is basically proving all of these like fundamental, foundational, gotta understand it sort of things, but it goes through and proves it all. Pretty challenging course for sure, but we will absolutely use these relationships, and more specifically, those that have been through this before, we're going to use this a lot, right? Definite integral from a to b of f of x. Anyways, so that was part of the little intro video that you guys had for, I think it was for last time. And we got this one right here. I thought this would be one more time. It says write a Riemann sum equivalent to that. It's another chance to do another type of these. So let's do what we did at the start of class. Will you guys try this one again? Or this one, again, like you did the first one. Same concept, just new function, new details. See how it goes. I hope that it goes well. Be around to help you if you would like. Okay, up here I'm going to do the easy part. Okay, I want to hear from you guys. Anybody have suggestions on what we should write next? Sorry? No, you can't do sigma of dne, I'm sorry. Any suggestions? What would you write next? 4 over n. Agreed. So that is the base of each rectangle that would go and span across this region. Suggestions on what comes after that? 5. Okay. Then what? Open parentheses. -3 plus 4 over n. I? Yes. Completely agree. So notice this is different, right? Our starting value, I think for the first one was 0, and I think for the second one our starting value was 1. So notice here the starting value for our input is -3. Also, I think on the first two we tried, the whole interval width was just 1 in both cases. Here the interval width is 4, so our base length is 4 over n, 4 over n. So those are some differences between the two, between this and the two examples we've previously done. So I'd love to answer any questions for you on that one. Yeah, there we go. Anything? Okay, fair enough. Let's keep rolling then. We're into 4.3 here, and yes, right here. Okay, so this is where kind of your understanding of concepts really comes into play. There's no way that area can be negative. There's no way that area can be negative. You think about like your house, the square footage of your house, it's all positive square feet, right? Positive area. Even if your room is a total mess, still positive square feet, right? You cannot have negative area. So we're never going to say the area is negative such and such. But if you're looking at a graph like that, there will be some integrals, some definite integrals that will produce negative numbers. Why? If area is never negative, why would a definite integral spit out a negative number? Something about backwards, which is possible. Below the x-axis, also possible. Okay? Let's remind ourselves what a definite integral is. A definite integral is simply an infinite summation of really skinny heights, right? An infinite summation of these really skinny little rectangles. And so if you tell the integral to add up a bunch of positive numbers, guess what's going to come out? And if you tell an integral to add up, a definite integral to add up a bunch of negative numbers, what's coming out? A negative, right? That's all it's doing is just adding up all these either positive or negative or a combination of the two numbers. So if we were going to look at something like the integral from -4 to -1, that is looking at this region down here that I'm highlighting in purple. So while area is never negative, wouldn't the integral spit out a negative value for this? Simply because all the numbers that are being added up are negative. The area is below the x-axis. So if we actually did this, what would you get? Looks like it's a triangle, right? We can use area here. So what's the base length on the triangle? 3. And the height is 4. So the area is 6. And since we're below the x-axis of the region, -6. Okay. I think it's worth saying at this point. I would strongly encourage you, if you're doing the integral of f of x and you have a nice piecewise graph like this, please do use geometry. Please do use area to help you evaluate something like that. Once again, at the reading this last year, I found people that did a problem like this, and they found the equation of that line segment. And then they found the equation of that line segment, and they did 2 separate integrals over the appropriate domains and did it correctly. And it was amazing. They did it all correctly, and the pressure of the test and everything. But I bet it took them like 12 minutes at least to get all that stuff right. Whereas they could have just been like, base times height times divided by 2, 6, right? So be efficient with what you're doing, both on my tests or any other like AP sort of tests. Any questions there? Okay, next one, the integral from -4 to 2 would stretch from here to here. What would you guys think that the integral would spit out on this one? Negative 0? Negative 0. Just remember, 0 is the Switzerland of the numbers. It has no sign. It's just 0. It does not take a side. Now, why on earth would that be 0? Well, because this is going to be, this will integrate as a negative 6. This will accumulate positive 6. And as you accumulate all the way across, those two would add themselves out to be 0. That make sense?
Yeah.
Okay. And then the last one is the integral from negative 4 all the way over there to 4. So if we just include this one right here, we just have to think about what this last triangular area is. Negative 4. So the areas for the integral will spit out a negative 4 for that part. So what would you guys guess the final answer would be? Yep, 0 plus negative 4. You could think of it as negative 6 plus positive 6 minus 4, which is just negative 4. So the last thing I'm going to ask here is a very common question. Very bottom there it says, find the total area. Really important phrase there. Find the total area enclosed by the graph up there of f of x and the x-axis. So find the total area. So let's establish a couple things. Number one, area can never be negative. And can't we look at this and say, well, if we're finding the total area, isn't the total area going to be non-zero? Because you can see that there's some area, right? Mm-hmm. So what do you guys think the area, the total area enclosed by those two things would be? 16, right? Wouldn't you say, well, the first area is 6, and the second area is also 6, and the last area is 4, and those do add up to be 16. And again, it's the phrasing of the question. I didn't ask what the integral from such and such to whatever would be. I just said, what's the total area? Area could never be negative, and so we just think of all those areas we found as being the positives that they are. But the integral would still spit out negatives, right? So there's a difference between a definite integral versus only considering area. Liz?
So if you wanted to write that like as an integral, would you just put absolute value signs around the f of x dx? Would that mean the thing that you want it to mean?
Sure. So if I did this, this would be a way to express what the last question is asking.
Okay.
Yep. For sure. Anybody else? I think we got a couple of properties coming up. They're all pretty intuitive, I think. Am I right? Yes. All right, so some properties of definite integrals. Like I said, I'm hoping these will be pretty intuitive for you. All right, number 2, the integral from a to a. To me, it really helps to think about area here. So if the lower limit of the definite integral and the upper limit of the definite integral match,
0.
well, we're not really accumulating any area, are we? So the answer to that would be 0. You are correct. So believe it or not, those maybe that are AB veterans might recognize this. Every now and then, maybe not directly but indirectly, you will get something like this, ask you to evaluate an integral like that. And if you wrote it out, hopefully knowing this property, this would be super easy. The answer would be 0. Number 3, the integral from a to b is the exact same thing as the opposite of the integral from b to a. In other words, if you switch the limits, you can switch the sign. There's a deeper reason for that. It has to do with the fundamental theorem of calculus and the subtraction that comes out of that. You're just basically changing the order of the subtraction. Bottom line is an example. The integral from 5 to 2. Normally, don't we have the lower number actually be the lower number? Because we usually accumulate from left to right, although you can accumulate the other way. We're used to having the lower number actually be the lower valued number. So maybe you would want to do this negative integral from 2 to 5 of f of x dx. That might make sense to do, although you can accumulate the other way, and that's okay to do. Any questions? Okay. Next couple here, numbers 4 and 5 and 6. I'll try to fit these. There we go. I like an area argument here for number 4. If I've got the integral from a to c, that would be the whole area. Wouldn't that be equal to the two little parts added together? So if I said integral from a to b, that would be this little segment here, and then the integral from b to c would be that little segment. So all this is really saying is that the green part plus the red part equals the whole thing. guys okay with that? Yep, okay. So an example here, what would you guys say that expression would be equivalent to? This one right here?
1 to 7, integral 1 to 7,
Thank you, Jasmine. I agree. Absolutely. Okay, and then a few more here. Number 5, integral from a to b of k f of x. So k typically stands for a constant. It's a constant multiple. What can you do with the k?
Take it out.
Take it out, do whatever you got to do, and then you multiply back in, right? So I would say k integral from a to b of f of x. So in the example, which number gets to come out of the integral? 7 does, yep. So 7 integral from -5 to 8 of f of x dx. Might make it easier. There are plenty of examples where that would be a good move. And then finally, number 6 here. If you have the integral of a sum or a difference, then you can simply go integral of each term individually. This is not true of multiplication or division or something like that. But here you can just say the integral of f plus g or f minus g would be the integral of f minus the definite integral of g, like so. This is a very handy property, especially when we start getting into composites or other integrands that have very different characteristics. This really, really helps. And I think our example is actually a pretty nice example of that. Can you see how someone might be tempted to look at that 5 and say, that's a constant multiple, let's get it out? Do you see why that would be an error if I did it that way? Because all of a sudden, wouldn't the 5 be times everything in the integrand? And it's not accurate. So if we split this up, we can fix that. So this would give me the integral from 3 to 4 of x to the 5th dx plus the integral from 3 to 4 of 5 sine of x dx. And then if I wanted, couldn't I get the 5 out now?
No.
Now that would actually work. That would make sense. One other note, can I show you this real quick? Be really careful when you were writing something like this. If I wrote the integral from 3 to 4 of x to the 5th plus the integral from 3 to 4 of 5 sine x, what's wrong with what I just wrote? Yeah, the dx. This really has a totally different meaning, right? Think of this integral sign and the dx as the opening of a parentheses and the dx as a closing of the parentheses, right? And so if you did it this way, you're basically saying that this whole thing right here is your integrand, and that's not the case. If you put the dx right there, then now it's clear what you're actually doing. So be careful with that for sure. Anybody have any questions? Okay, so I think there might be a couple of examples to work through here. There's not. We're into 4-4. This is good. It's good. So if you looked at the calendar, if you looked at Schoology, you know that we're going to camp out in 4-4 for a while. 4-4 has a lot of stuff going on. I hope that you've watched the intro video or you're an AB veteran and you remember all this stuff. But anytime something is called the fundamental anything, and it's probably important, right? Fundamental means this is the stuff, right? This is the stuff you got to know. This is the takeaways. For example, having been through the math you've been in, wouldn't you agree with me that a fundamental skill of an Algebra 1 student would be they better be able to solve a linear equation? Like if an Algebra 1 student, like getting ready to finish Algebra 1, and they see 3x plus 7 equals 10, and they think to themselves, I have no idea how to do that. Maybe they should repeat Algebra 1? Just saying. They probably should, right? And so fundamental, I look at this in a similar way. If somebody doesn't understand the fundamental theorem of calculus, maybe not like fully immerse themselves and be able to write a thesis about it, but if they don't know what it means and how to use it and how to do stuff with it, then they probably didn't learn as much calculus as they should have learned. That makes sense? It's fundamental. Got to know this. All right, so a little video takes us through a couple of ideas there and then an example. And looks like I want to do number 2. I do. Okay, so based on what you saw in the video, I would say that number 2, or maybe what you've done in the past, number 2 is very accessible. So please try number 2. Ready. I want to make sure that you guys are all clear on notation. And that'll probably turn you loose a little bit, and we'll just kind of see how it is all going. So as you saw in the video, if you're finding a definite integral by hand like this, then the very first thing you want to do is find the antiderivative. And maybe, just maybe, did anybody bring the 3 out? Because you could. You might just mentally do it. You don't really have to do it on paper. You can just do it in your head, but whatever. So then I'm going to find my antiderivative. The antiderivative of x to the 1/2 would be 2/3 x to the 3/2. And then kind of the standard notation is this. You don't want to lose the from 1 to 4 thing. At this point, we have done the definite integral. Or excuse me, we've done the indefinite integral. We found the antiderivative. But I got to finish with the definite integral. That vertical line with the 1 and the 4 means evaluated from 1 to 4. So one thing you don't want to do is this. This is definitely incorrect. Seen people do that before. Haven't you already done what the tall skinny s told you to do? You found the antiderivative, right? So we're not going to do that. We're going to go vertical line from 1 to 4. Okay, the 3's cancel out. So this gives me 2x to the 3/2 evaluated from 1 to 4. So the fundamental theorem of calculus tells us that we can find this, the value of this, by plugging in the 4, plugging in the 1, subtracting in that order. So it'd be 2 parentheses 4 to the 3/2 minus 2 parentheses 1 to the 3/2. And I don't know, there have been times in the past when I've had really good math students look at 4 to the 3/2 and be like, what? How do we do that again, right? And so just remember that the denominator is your root. I always do that first. So what's the square root of 4? Cubed is?
Wait, you can do the root first?
I always do the root first, yeah.
That's so much.
16, yeah, because it makes the number smaller and then bigger instead of even bigger then smaller, yeah. So 16 minus 2, because 1 of the 3/2 is just 1. I got 14 for this one. What do you guys think?
I would do the square first, too. Like, I would do the 3 before the 2.
I like to make it instead of... Anyway, your choice. It works either way. Okay, would you guys please try numbers 3 and 4? 3 and 4. 3 is very straightforward if you know your rules. 4 takes a little bit of work. So please give it a try. Number 3 either took you forever or you knew it pretty quick, right? Because I think if you know your derivative rules, you would probably recognize that integrand pretty fast. So if you didn't, this is just a chance to remember and go back and review again. So the derivative of what is secant squared? Tangent. And so the antiderivative of secant squared had better be tangent. So my first step would be to write my antiderivative, tangent of x, evaluated from 0 to pi over 4. This is definitely a no calculator sort of a question. So as I complete fundamental theorem of calculus part 1, tangent of pi over 4 minus tangent of 0, we got to turn to the unit circle. What's tangent of pi over 4? Uno. What's tangent of 0? 0. Therefore, our final valuation for this would be 1. Any questions on number 3? We throw around unit circle type stuff as if you should just know it, and maybe you should, but if you don't, something you want to work on, if you want to work on it with me, you're certainly welcome to do that. I have my way of doing it that I like. You might have a different way. We can figure out a way for you to remember it well. Number 4, what'd you do with number 4 before you started doing calculus-y kind of stuff? Yeah, and Emma, what'd you do specifically? Flip up and distribute. That's right. So integral from 0 to 9, 2x plus 1. And then you got to be really careful and write that as x to the negative 1/2 because you got two things going on, right? You're turning the radical into a rational exponent and you're moving from bottom to top, so the exponent's got to go from positive to negative. So a lot of times you do two things, you forget one of the two. So be careful with that. As Emma suggested, oh, by the way, stop talking. Listen for just a second. Do you realize that if you start to find your antiderivative right here, you're going to have issues, right? Because it's a product. And we're going to learn new skills to deal with integrands that are products. We haven't learned how to deal with this one yet, and so you have to distribute. You do not have a choice, so please do what Emma suggested and distribute. So integral from 0 to 9 of 2x to the positive 1/2 plus x to the negative 1/2 dx. And maybe this would be an excellent opportunity to apply one of those properties. Maybe we rewrite this as integral from 0 to 9 of 2x to the 1/2 dx plus integral from 0 to 9 of x to the negative 1/2 dx. Why on earth would I do that? Now you can take out the 2. Before, you really couldn't take the 2 out without doing some special stuff with the second term. So maybe you do it this way. Maybe you don't. You really don't have to. So it'd be 2 times integral from 0 to 9 of x to the 1/2 dx plus the same thing from before. And now I'm trying to show you a lot of little steps here. Maybe you need to show all these. Maybe you don't. Just want to put them out there for you. We need to do our antiderivatives. Jaden, what is the antiderivative of x to the 1/2?
That would be 4 x to the 3/2.
X to the 3/2. And what was the first thing you said?
Well, I put the 2 out, but it's 2/3. There you go.
2/3, yeah. Agreed. And that's evaluated from 0 to 9. Okay. Jeff, how about the antiderivative of x to the negative 1/2? Got it. Also evaluated from 0 to 9. Be really careful. I know AB people, it's really easy to get into this rhythm that anytime one of the two limits is a 0, we just automatically think that that term will 0 out. And that is the case here. But if you're dealing with sines or exponentials or cosines or logarithms and stuff like that, then that will likely not be the case. So be careful with that. Here I've got 4/3 times 9 to the 3/2 minus 0 plus 2 times 9 to the 1/2 minus 0. What's 9 to the 3/2?
27.
And 27 times 4/3 is? 36. Plus 9 to the 1/2 is 3 times 2 is 6. Do you guys get 42?
I did now.
I hope I didn't make any arithmetic errors.
Yes. Yeah.
Is that right?
Yeah.
Okay. Any questions from anybody about any part of that? I'm so excited to see what's next. You ready? You ready? All right, here we go. What's next? Oh, yes, a piecewise graph. So, hey, listen, one of the little known, or not little known, but little acknowledged conditions for doing, bless you.
Bless you.
Bless your soul.
One of the rarely mentioned conditions for evaluating a definite integral is continuity. You've got to have a continuous function on the interval that you're dealing with in order to evaluate. Hey guys, listen up. Come on. To evaluate a definite integral, you got to have continuity. And there are ways around that, and this is going to be one of those ways. Later on, we're going to be working with integrals of functions whose graphs have like vertical asymptotes. And so that's clearly a discontinuity, and how do we deal with that? Well, we'll get to that stuff later. This clearly could be discontinuous. We don't know yet. We could look at it and decide. But it is piecewise, and so that's going to kind of necessitate a little bit of a strategy change from what we've been doing. So I don't know. I feel like you can probably do this. And if you can't, I'll fill you in a little bit. But give it a shot. See if you can figure out what the definite integral from 0 to 2 of g of x would be. The reason why this is a challenge is because I'm sure you noticed if we're doing the integral from 0 to 2, do you guys see how the joining point between the pieces is right in there?
Yes.
It's in between the 0 and the 2. It would be really tricky and perhaps worth asking sometime to give you a piecewise and then say, maybe if I gave you this exact piecewise and said, find the integral from 1 to 3. Because then essentially wouldn't you be ignoring one of the two pieces?
Yeah.
Right? So it'd make you think a little bit. But anyways, that's not the case here. The 1/2 is within that interval. So I would say something like this. Integral from 0 to 1/2 of sine of pi x dx plus the integral from 1/2 to 2 of negative 4x plus 6 dx. So that would be my setup. And like I mentioned a second ago, this is a very doable integral. You can totally do this without a calculator on paper. But this composite input, the pi x, puts us a little bit past where I want to go. So I thought the calculator, so if you haven't already broken out the calculator and done Math 9 with this, Jeff, this would be a good opportunity for me to show you kind of, or did you already do it? So here's what you do. You have a little bit of a different syntax. You're going to go math 9. So this means numerical integration. So here's what you do. I'll just do the first one. You would just go sine of pi x, comma, oops.
There you go.
I want to get rid of that. Comma, x. So that's kind of like the dx.
Yeah.
You're saying I want to do this with respect to x. Comma, 0, comma, 0.5. I lost a comma, Jeff. There we go. That makes sense?
Yeah.
So you're saying, here's my integrand with respect to x, low limit, comma, high limit. So what that does is that finds your antiderivative and then goes evaluation of the big number minus evaluation of the small number, does it all for you. So if the calculator's active, that's exactly what you'd want to do. That makes sense?
Yeah.
And then you just do the same thing with the other one. You add the two numbers up and you get the final value for that integral. Is that good? Yes, ma'am.
Sorry. Yeah, I was like, what?
Depends on when it showed up. If it showed up anywhere before us doing 4.5, then I have to do it that way just because you hadn't officially learned how to handle the sine of pi x yet. But absolutely, once, like if, could this be, say, an AP test question or a semester 1 final exam question? For sure without the calculator. Yep. I wouldn't expect you to get this done in like 2 minutes,
Yeah.
right? Because there's a lot of details to be worked out with the pi, and then you got to multiply by 1 over pi, and so I wouldn't look at this and be like, oh yeah, they'll be done real quick. But you could definitely do it. In fact, questions like this have been on the AP test, the FRQs. Hey, one thing I want to make really clear. Hey guys, listen please. This will save you from pain and suffering and tears and frustration. So I was just talking with Jeff about Math 9, and I think he's good, and Jaden's okay with Math 9, right? Rest of you guys okay with Math 9? I mean, honestly, you kind of wore those buttons out last year, I'm sure, if you're doing things right. So I want to be really clear about this because, like I said, I don't want you to get frustrated. What was the answer, by the way? 1.81818? Okay. So listen, please. If this were calculator active, you got to get this. I'm sure you know this, but if you don't listen, this would be sad for you. If this were calculator active and the only thing you wrote down as an answer was the thing in the purple box, how much credit would you get?
1.
None. 0. Nothing. No. No. You would not. I'm sorry, Jasmine. I truly am. The reason is again, I know that the end focus is the AP test. We don't really talk about that till April. But if I start training you in April, if I wait until April to start training you for that stuff, I feel like I've done you a disservice. On the AP test itself, they actually have a word for this. They call this a bald answer. Bald answer, and bald answers almost always get nothing, especially in a scenario like this. If you wanted to get full credit, all you have to do is put the stuff in both purple boxes, and you would get full credit. So if you're about to type, here's the rule of thumb. If you're about to go Math 9, and you don't have the thing that you're just about to put into Math 9 written down on your paper, be prepared to get no credit. Make sense? If you're about to do Math 8, and you don't have like f prime of 7 equals like written down on your paper, be prepared to get no credit, whether the answer is correct or not.
If
I want to
that's,
see.
not the main part of the question, like that's just something you have to do like in the question. Can you do something to write it down?
I kind of think I know what you're talking about. Like I can think of some definite integrals that are just sort of like steps along the way to finding like a max or a min or something like that. I would still write it down. So like at the reading itself, people think that it's always the same rules. It's not. Year to year, some questions will be graded this way, some are graded like this way, others are graded like that way, just a little bit. Yeah, it just depends on the number of points that are allotted, and so it's best to always show setup. All right, where are we going? Yes. Okay, this will be a good place to finish. We'll do this one, and we'll pick up after this tomorrow. Yes?
Yeah, sorry, I just had a question about the previous thing.
Go ahead.
Is it even possible to find it because it's not academic?
Did you? Sorry, we talked about that at the start, guys. Listen up, please. We talked about that at the start. I didn't really come back around to it. Is it continuous or not? I don't remember.
It's not.
Over to. Yeah, it's not continuous. So the way we get, how we get around that? Is we split it up into two pieces. Right? Because the first piece had a continuous function for the integrand. The second piece had the continuous function for the integrand. We can do those two separately. We add them up and we get the final result.
So continuity doesn't matter.
Continuity does matter. It does matter, but we got around that by splitting it up into the two parts that actually were continuous.
So even if it's not continuous, you can still...
Yeah, like the area doesn't leak out. So like if you had, I don't know, let's say that this was 1/2. Let's say it did something like this. I don't know if that's accurate or not. And we were finding this area from here over to like here. The area doesn't like leak out right there. We're starting at 1/2, we're moving over. So we can still do that as long as we split it up appropriately. The farmer needs to optimize his field. You're right. No holes in the field. Okay. Hey guys, let's finish with this. You all know how to find an average. Don't you just add up everything and then divide by the number of numbers?
That's usually what I would do.
The issue with this, if I were to say, that's what goes right here. You add everything up, add, then divide by the number of numbers. That's how you find an average. What is an integral? You guys remember from 5 minutes ago or half hour ago? Say again? Well, so an antiderivative, yes. What is? Let me put this word in here just to make my question a little more clear. What is a definite integral? What is a definite integral? It's not an antiderivative, it's more than that.
The area under.
And how do we find the area under the curve?
By finding the area of infinitely small rectangles.
Oh, now we're starting to talk. Okay. Infinitely skinny, not small. So what is an integral? It's an infinite summation. Infinite summation. There we go. I think I can spell. So here's the issue. Here is why this would be in a calculus course, because you look at the word average and you're like, well, isn't that more of like an 8th grade concept or whatever? It's not that hard to do. Here's why it's in calculus, because if you think about some function, and let's say that function has a physical meaning or not, regardless, let's say that I've got this interval from like A to B, and I say, all right, let's find the average of the y values. How would you go about finding the average of the y values of that blue graph from A to B? Like you guys said earlier, you add up the numbers and then divide by the number of numbers, right? Well, so how is this going to go? It's not going to go well, right? Because how many y values are there from here to here? So you need to add up an infinite number of y values. Good luck. Right? You're going to die infinitely short of your goal, right? It's not even going to be close, right? So we turn to a much better tool for the job, and that would be the definite integral, because that will add up an infinite number of infinitely skinny little rectangles, right? That's kind of the whole point here. And so the way that you find the average value of a function is, like you guys suggested, you add up all of the y values by doing this. The integral from a to b of f of x dx. It'll add up all the y values, but you still got to divide, right? Here's how you divide. Multiply by 1 over b minus a. By dividing by that b minus a value, this will give you the average value across that interval from a to b. And for those that know this from last year, this sets up all kinds of interesting issues with units when we start looking at these in context. So we'll deal with that stuff when we get there. What I'm going to do is this. I'm going to leave you guys with this. I'm going to set this up for you, have you guys set it up with me here, and then I'll see if you guys can finish it out. So if I'm going to find the average value of f of x on the interval from 1 to 4, I would say that that is equal to the 1 over 4 minus 1 times the integral from 1 to 4 of f of x dx. So give me the average value of that curve. It's a parabola. It'll give me the average y value on the interval from 1 to 4. It'll add up all the numbers, all infinity of them, if you will, and then divide by 3, which is the width of the interval. So take a minute. Think of this as maybe like a speed round. You have 3 minutes. Maybe you can do it. We should race. Here we go. No calculator.
But I also
Yay.
waited for the start.
I think I got 16.
Yes.
All right. Speed math is fun. Just throw caution to the wind and go fast and hope you didn't make any little arithmetic errors.
Can you solve that in your head?
Solve what?
Just the 1/3 times x cubed minus x squared on an integral from 1 to 4. Can you
Probably, yeah.
cut out the last 2 lines?
I think it's faster to write because I'd sit there and I'd be like, okay, 4 cubed 64 minus 4 squared is 16, 48, 1/3. By the time I was done thinking about that, I'd probably have it down on paper. I don't know. It'd be pretty close. It'd be pretty close, I suppose. I'm used to just writing out all my steps because that's what I'm used to like getting you guys to do. But it's a fair question. I do love those math contests. It's so fun. I've got a whole bunch of notebooks full of that stuff.
When you're at home for fun, do you ever like try to speed run one of these?
Oh, all the time. So yeah, like when I'm making your guys' tests,